Welcome back. We are going to prove a very important theorem for cyclic groups. G is a group, A is an element of G, and A has order n. Um, for any positive integer k, we have that the subgroup generated by a to the k is equal to the subgroup generated by a to the power the GCD of n and k, and the order of a to the k is the same as n over the GCD of n and k. In other words, the order of a to the k is the order of a divided by the GCD of k and the order of a. Okay, so first I'm going to go ahead and prove this equation here. To do so, we're going to show, to simplify the notation here, let me denote the GCD of n and k by d. And to show this equation, then we have to show that the subgroup generated by a to the k is a subset of the subgroup generated by a to the d, and the subgroup generated by a to the d is a subset of the subgroup generated by a to the k. Okay, let's first show this. So if x is in the subgroup generated by a to the k, then x is some power of a to the k, let's say a to the k to the a, which is the same as a to the k times a. Now k is divisible by d, so we can write k as a multiple of d. So this exponent ka can be expressed as a multiple of d. So a to the d times some integer a prime. And that's because d divides k. And so we obtain that x is a, so this is a power of a to the d. So then x is an element of the subgroup generated by a to the d. Okay, so that shows us that the subgroup generated by a to the k is a subset of the subgroup generated by a to the d. But now I want to do the opposite. So if x is in the subgroup generated by a to the d, then x is some power of a to the d. So let's say a to the d to the m, which is equal to a to the dm. Now d being the GCD of n and k, by using the extended Euclidean algorithm, we can express d as a linear combination of n and k. So let's say d is nx plus ky. Then we can rewrite that as a to the nxm plus times a to the kym. Now a to the nxm, that's just the identity because a to the n is the identity, n is the order of a. So we get a to the power kym, and a to the kym is the same as a to the k to the power ym. So we see that if x is in a to the d, if x is in the subgroup generated by a to the d, then x can be expressed as a power of a to the k, but then it means that x is in the subgroup generated by a to the k. So that shows that the subgroup generated by a to the k is equal to the subgroup generated by a to the power the GCD of n and k. Okay, so now we have to show the next equation. To show that the order of a to the k is equal to the order of a divided by the GCD of k and the order of a. Again, we're going to let d to denote the GCD of n and k. So we want to show that the order of a to the k is n divided by d. But since we have already shown the first equation here, the first equation is the subgroup generated by a to the k is the same as the subgroup generated by a to the d. So the order of a to the d and the order of a to the k are the same. So all I need to do is find the order of a to the d. Now we're going to show that the order of a to the d is n divided by d. So notice that here I have d in the denominator. So how do I show that the order of a to the d is n over d? Well, first of all, notice that the a to the d to the power n over d is equal to a to the n, which is the identity. So the n over d, this power of a to the d gives us the identity. So now we have to show that n over d is the least power of a to the d that's equal to the identity. So we need to check that. We need to check if this is the least power of a to the d that equals z, the identity. Indeed, if it were the case that a to the d to the m is the identity for some m less than n over d, then we would get that a to the dm is the identity where m times d is less than n. But this contradicts the fact that the order of a is n, right? Because the n is the least power of a that gives us the identity. So, but here I have dm, which is less than n. So it contradicts the order of a being n. So we see that n over d is the least power of a n over d is the least power of a to the d that is equal to the identity, and hence the order of a to the d is n over d. So the order of a to the d is n over d, which is the same as the order of a to the k, because the subgroup generated by a to the k is the same as the subgroup generated by a to the d. So the order of a to the d is the same as the order of a to the k, which is equal to n over d. So that completes the proof of this theorem. Okay, so let me stop here because we already have 7 minutes here. In the next video, we'll be looking at a couple of consequences of this theorem.